In this video, I will explain 3 different methods for shape detection in a point cloud. The aim of these methods is to automatically detect simple shapes such as lines, planes or cylinders in a point cloud. I will start with a short example. Here we see a point cloud of a building. With shape detection we are able to detect the 4 planes that occur in this point cloud. You can see that I assigned a unique color to each plane instance and the respective fitting points. One application of shape detection is object reconstruction. Here you can see that the detected planes can be used to reconstruct a mesh model for this building. I will explain 3 different shape detection methods: ransack, region growing and the half transform. Notice that all these methods can be used to detect a variety of shapes. However, in this video I will only show examples for line detection and plane detection. The first method that I will discuss is ransack. I will now explain how to detect a line in this 2D point cloud using ransack. There are 3 steps in the ransack algorithm. In the first step, we randomly pick a so-called minimal set of points needed to uniquely define our shape. In the case of a line, we need 2 points. In the second step, we create a line instance from the picked minimal set. And in the third step, we count the number of inliers. This is done by counting how many points are within a distance epsilon from our line. The total set of inliers is called the consensus set, and the number of points in the consensus set is called the score. As you can see, this line has a score of 4. Notice that we don't count the blue points from the minimal set. Now, the algorithm will keep repeating these 3 steps each time, starting with a new randomly picked minimal set. For instance, this minimal set, with these inliers, has a score of 9, which is the best with this epsilon for this point cloud. Finally, the line instance with the highest score is outputted by the algorithm. I will now explain how to perform plane detection in this 3D point cloud using region growing. Notice that each point has a normal vector. These normals can be estimated by fitting a plane to a point's local neighborhood prior to running the region growing algorithm. Region growing works by gradually growing a region of points that belong to the same shape instance. In this process, neighborhood queries are used, typically implemented using a KD tree. The algorithm starts by selecting a so-called seed point, marked in blue here. This is a point that we suspect to have a good fit with one plane instance. With this point we start to grow a new region. To start growing the region, we do a nearest neighbor search from the seed point. In this example, we use a KNN search with k equal to 4. The resulting points are called candidates, and for each candidate we perform a test to see if it should be added to the region. In this example for plane detection, this test entails computing the angle between the normal of the candidate point and the normal of the seed point. If this angle is below a given threshold alpha max equal to 5 degrees here, we add the candidate point to the region. Notice that in this example all the point normals in one plane are perfectly parallel, resulting in normal angles of 0 degrees. In practice, there will be small variations in the computed angles. The process of finding and testing candidate points is repeated once for each point that is added to the region. Candidate points that have already been assigned to a region can be ignored. When we encounter a candidate point that fails the test, such as this one here with an angle of 90 degrees, we do not add it to the region. The region is completed when all the points inside it have been processed. At this point, a new seed is selected and used to grow a new region. The region growing algorithm stops when there are no more seed points. Now we will look at line detection on a 2D point cloud using the half transform. But before we look at the algorithm itself, we need to choose a shape parameterization and we need to design an accumulator. We can parameterize a line using a radius r and an angle phi. In this case, r is the length of the line segment that connects the origin with the closest point on our line. Phi is the angle of that segment with the positive x-axis. The accumulator is a matrix, with each axis representing one parameter. In our example, the horizontal axis represents the angle phi, and the vertical axis represents the radius r. Our accumulator has a size of 9 by 2. You can see there are 9 possible values for the radius and only 2 possible values for the angle. Restricting the possible values of the parameters like this is called quantization, and it is needed in order to make the algorithm computationally feasible. Notice that our example accumulator is extremely small, and as a result it can only represent horizontal and vertical lines. In practice, the accumulators are bigger and have a finer quantization. Notice that each cell in the accumulator thus represents a unique line instance. For instance, this cell represents this line, and this cell represents this line. Now we can finally get to the half transform algorithm itself. The basic idea is to iterate over all the points in our point cloud and then to check for each point which instances from the accumulator fit with that point. Recall that our accumulator only does vertical and horizontal lines, which will be drawn in red and blue respectively. Now we determine for each input point what shape instances from the accumulator are fitting. For instance, for this point we can fit this line corresponding to this cell in the accumulator, and this line corresponds to this cell in the accumulator. We then increment these cells. Indeed, the cells in the accumulator are used to count the number of input points that fit the corresponding shape instance. The process is repeated for the remaining input points. And finally, the accumulator cells with the highest values mark the detected shape instances, in our case these two lines.